Hello, and welcome to a new lecture. In this lecture, we will explore three essential topics in secure software development: application programming interfaces, or APIs, input validation, and code analysis. These elements play a critical role in ensuring that software applications are not only functional, but also secure against the growing range of threats in today's cybersecurity landscape. APIs enable communication between different systems and software components, while input validation ensures that user input is checked for security before being processed. Code analysis, on the other hand, helps identify vulnerabilities in the code base itself. Let's explore these concepts in more detail and understand how they contribute to the overall security of an application. Application programming interfaces, or APIs, have become a fundamental building block of modern software applications. APIs define the way software components communicate with each other, enabling applications to access data, functionality, and services from other systems or applications. While APIs provide many benefits, such as enabling integration with third-party services, enhancing modularity, and improving scalability, they also introduce security risks if not properly designed and implemented. An insecure API can serve as an entry point for attackers to exploit vulnerabilities, steal data, or manipulate services. One of the key risks associated with APIs is exposed endpoints. If an API exposes sensitive endpoints without proper security controls, attackers can easily gain unauthorized access to critical data or services. To mitigate this risk, it is essential to use authentication and authorization mechanisms for API endpoints. This ensures that only authorized users or systems can access certain endpoints. Strong authentication methods, such as OAuth or open authorization, API keys, and certificates, should be used to control access to sensitive endpoints. Additionally, API responses should never contain sensitive information such as passwords or tokens unless they are encrypted. Another security concern with APIs is input validation. Since APIs often accept user input from various sources, it's crucial to ensure that input is sanitized and validated before being processed. Unsanitized input can lead to several types of attacks, including structured query language injection, cross-site scripting, or buffer overflow. Developers must implement robust input validation mechanisms that check the format, type, length, and value of incoming data. This prevents malicious data from being processed and safeguards the integrity of the application. Additionally, rate limiting and throttling are important techniques for securing APIs. These measures help prevent denial of service attacks, where an attacker overwhelms the system with excessive API requests. By limiting the number of requests that can be made within a given period, organizations can ensure that their APIs remain available to legitimate users while minimizing the risk of service disruption. Now, let's move on to input validation, which is one of the most effective ways to prevent attacks that exploit user input. Input validation refers to the process of checking incoming data to ensure that it is safe, expected, and does not contain malicious code or commands. It is a fundamental practice in secure coding because improperly validated input can lead to serious security vulnerabilities. Input validation should begin with whitelisting, where only known, good input is allowed, rather than relying on blacklisting, which tries to block known malicious input. For example, if a user is expected to enter an email address, the input should be validated to ensure it meets the expected format. Any input that does not match the expected format should be rejected. Input validation should be applied to all user-supplied data, including data from forms, URL parameters, HTTP headers, cookies, and even data from third-party sources. A common attack vector is structured query language injection, where an attacker injects malicious structured query language code through user input, attempting to gain unauthorized access to a database. To prevent structured query language injection, developers should use parameterized queries or prepared statements, which separate user input from the actual query logic, ensuring that user input cannot alter the intended functionality of the query. Another significant attack is cross-site scripting, which occurs when an attacker injects malicious scripts into a web application's output, potentially leading to data theft or session hijacking. To defend against this, developers should sanitize and encode user input to ensure that any potentially harmful code is not executed within the user's browser. For example, characters like less than, greater than, and ampersand should be encoded to prevent them from being interpreted as HTML or JavaScript. Input validation should also check the size and length of the data to prevent buffer overflow attacks. By setting appropriate limits on the size of inputs, developers can avoid situations where malicious input causes the program to overflow its allocated buffer, potentially leading to system crashes or exploitation. Moving on to code analysis, which is an essential practice for identifying vulnerabilities in the software development lifecycle. Code analysis refers to the process of reviewing the code base to identify potential security flaws, bugs, or areas of inefficiency. Code analysis can be performed manually or using automated tools that scan the source code for patterns that indicate common vulnerabilities. There are two primary types of code analysis: static code analysis and dynamic code analysis. Static code analysis involves examining the source code without executing it. Automated tools scan the code for known patterns of vulnerabilities, such as insecure data handling, untrusted input, or poor encryption practices. Static code analysis is effective for detecting coding errors and security flaws early in the development process, allowing developers to fix issues before they become more difficult to address. Dynamic code analysis, on the other hand, involves analyzing the application while it is running. This type of analysis focuses on how the application behaves in real time, including its interaction with the operating system, network, and external components. Dynamic code analysis tools can detect vulnerabilities that may not be apparent in the static code, such as memory leaks, performance issues, and runtime security flaws. Dynamic analysis is useful for identifying issues that only arise during execution, such as improper session management or insecure communications. Both types of code analysis have their strengths and should be used in tandem to provide a comprehensive understanding of the application's security posture. Static code analysis can be integrated into the development workflow through continuous integration tools to automatically scan code changes for vulnerabilities. Dynamic code analysis, on the other hand, is typically used during the testing phase to assess the application's runtime behavior. Code reviews are also an essential part of code analysis. Peer reviews of code can help identify potential security issues and ensure that the software meets security standards. By conducting regular code reviews, developers can ensure that best practices are followed, such as proper input validation, secure data handling, and efficient error handling. Code reviews also promote collaboration and knowledge sharing among team members, helping to improve the overall security culture within the development. To wrap up, APIs, input validation, and code analysis are all essential practices for building secure software. APIs enable communication between different systems, but they must be secured through strong authentication, authorization, and input validation to prevent exploitation. Input validation ensures that only safe and expected data is processed by the application, preventing attacks like structured query language injection and cross-site scripting. Code analysis, both static and dynamic, helps developers identify vulnerabilities and security flaws early in the development process, enabling them to build more secure applications. By incorporating these practices into the software development lifecycle, organizations can significantly reduce the risk of security breaches and deliver robust, secure applications.